Let us talk about basic computer architecture. And it's important to understand this at a basic level in order to appreciate some of the aspects of using R. Now, the heart of computers, digital computers, as we call them, is a device known as the central processing unit, or CPU. Now, in CPUs, modern computers have multiple CPUs, and these multiple CPUs are referred to as cores. The second most important thing in a computer is something known as random access memory, or RAM. And the random access memory, or RAM, is where um, data is stored. And so data can either flow from the RAM to the CPU, or it can flow from the CPU back to RAM. Now, in addition to the random access memory, or RAM, there is also a secondary memory, which um, on modern computers we call as SSDs, for solid state storage devices, or HDDs, hard disk drives. Um, and once again, data can flow from secondary memory to the random access memory and then onto the central processing unit, or it can come from central processing unit into the random access memory and then go to the secondary memory. Now, why have two different kinds of memory? The reason is that random access memory uses digital circuitry, and so it's very fast. So a random access memory can transfer gigabytes of data per second to the central processing unit. So it's fast. However, since it's based on electronic circuitry, it's also what's known as volatile, which means that when you turn power off, all the data in the random access memory is lost. On the other hand, secondary memory is slow. Um, in hard disk drives, you actually have platters that are magnetized and that store data, like vinyl records store music on them, and these platters are spinning relatively fast, up to 10,000 rotations per minute. Nevertheless, it's mechanical, and it's not as fast as the electronic circuitry of random access memory. And so secondary memory is slow, but secondary memory is non-volatile. In other words, when power is lost, when you turn the computer off, the data that's stored in secondary memory is not lost. For practical purposes, it's stored permanently. And that is why modern computers use this what is known as a memory hierarchy to store data, where you have a slow but permanent non-volatile secondary memory, where once we have produced results, produced output data, they're stored for posterity. Whereas When the CPU, the computer, is doing its computations, the data are actually stored in the random access memory because it's much faster. And the last aspect of computer architecture is that you have input devices. So these would be things like keyboards, mice, game controllers, and so on and so forth. And um, data flows from input devices into RAM. And then you also have output devices, and data flows from RAM once results have been computed into output devices, which are things like monitors and network devices to send data out onto the internet, and so on. It is worth discussing a little bit how data is actually stored in computers. Now, all modern computers are digital computers, and they're so called because the electronic circuitry in these computers can only exist in two states. So you could either have 5 volts or 0 volts, or you could have current flowing or not flowing. And this is achieved by these devices known as transistors. So all data in computers is represented in what's known as binary, which means you only have two symbols, 0 and 1. And where current is flowing, you might call it 1. And where current is not flowing, you might call it 0, and so on. So if we imagine the memory of a computer, you can sort of think of it as a library with bookshelves where each shelf holds one um, bit, and a bit can only have two values, 0 or 1. And so the RAM of the computer is going to be filled up with zeros and ones and so on. Now, 8 bits. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. 8 bits make up a byte. And each byte in the memory has an address. Just like in libraries, we use the Dewey Decimal System, which provides books and shelves addresses to locate them. Computer RAM also has addresses. So maybe this is the first location first byte in memory. So this might have an address of 1, and then the next byte might have an address of 2, and so on and so forth. Now, when we are writing code, when we are manipulating data, we have to tell the CPU to put data in RAM in particular locations. Now, modern computers might have 16 gigabytes of RAM, which means you have memory locations going up to 16 into 10 to the power 9, and it would be very, very difficult to remember these addresses. Therefore, programming languages provide something known as variables. And even though variables sound like the variables of mathematics, which are unknowns, actually, variables in computer science refer to memory locations, except when we create variables in programming languages. we can give them convenient names, so that we can remember those names easily, but the programming language in behind the scenes keep track of what is the actual numerical address of that particular memory location. So that's one of the things to to understand about computer architecture and how it relates to using R and programming. The other thing is, how do you represent different data in bits? Now, having a binary system with only two symbols, 0 and 1, means you can, it's like counting with two fingers. So in normal counting, we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now we have run out of symbols in the units place. So we put a 0 and then add the next number in the tens place, and then we continue and so on. So this is normal decimal counting where we have 10 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. But now if you have a binary system, then um, we if we start counting, we'll do 0 and 1, and we have already run out of symbols. Therefore, we will do what we did in decimal. We'll put a 0 in the units place and put a 1 in the next place. And the next number can be 1, 1. But we have again run out of symbols, so we will put zeros and put a 1 in the hundreds place. Therefore, 0 in decimal is just 0 in binary, 1 in decimal is 1 in binary, but 2 in decimal is 1 0 in binary, 3 in decimal is 1 1 in binary, 4 in decimal is 1 0 0 in binary, and so on. Now, um, what this means is, for things like integers, you can store numbers in memory as just a string of zeros and ones. For example, the number 42 will have the representation 101010. And if you keep counting in this table the way I was doing just now, you would eventually get to 42 and it'll turn out to be 101010. And so in memory, we will just store these bits, and we're off to the races. However, what will we do about um, signs when we have negative numbers? And the way that it is handled is, you reserve one bit, this bit, for the sign, so that if it is 1, it means the number is negative, and if the sign bit is 0, it means the number is positive. And so you will have the sign bit and then ones and zeros in other locations in memory. But then, how do you store characters, letters, A, B, C, and D, and so on? Since in memory everything is in the form of ones and zeros, we need some sort of code that converts these binary numbers into characters of English or other language. And that code is known as the American Standard Code for Information Interchange. And it looks something like this. where the the number 65 is used to represent A, 66 is used to represent big A, and 66 is used to represent big B, and the number 97 is used to represent little a, and so on and so forth. And therefore, by using a code, the ASCII code, we can represent symbols, non-numerical symbols in computer memory. And briefly, I would also mention how one might go about storing real numbers or rational numbers. And the way you do it is you will reserve 1 bit for the sign, as we did with signed integers, where 1 implies a negative number and 0 implies a positive number. Then we will reserve 7 bits for the exponent. And so we would be using something similar to the scientific notation where you have the mantissa times 10 to the power the exponent, and that exponent would be stored here. And then you would have 24 bits, which would store the um, mantissa or the significant bits. And in all, you will have a total of 32 bits to represent these numbers with decimal points, real numbers, including rational numbers or irrational numbers. Now, the broader point is that how some data is stored in memory depends on what type of data it is. So, integer data is stored in a particular way as a string of bits, and you can store character data as a string of bits, um, but use a code, the ASCII code, to convert between the decimal numbers and the symbols. Or you could use this kind of scheme of storing the mantissa and the exponent and the sign to store um, real numbers. And the technical word for such numbers as they're stored in computers is floating point numbers. Since each type of data has a specific way of getting stored in memory, each variable that we create during programming in R or in any other language also has a data type. And it's very important in order to write correct code to be explicit and know about which data type of both variable and data we are dealing with.